calculate cutoff frequencies and basically go through it that way. Now, today what I'm going to do is I'm going to show you how to use that information and apply it to something that's equivalent to a transmission line problems. And then we'll go into fiber optics. Well, we'll do slab waveguides just briefly, but then fiber optics. Slab waveguides are not that interesting, but at least you should be exposed. So next, before I start, any questions at all? Okay. So, let's see if this works. It does. Let's try green for a second. So now we're going to talk about applying a waveguide to a real-world problem. And Keenan, I forgot the waveguide again. I'm not going to go get it. But I may walk upstairs and get it and put it in my mailbox, so I can't forget it when I'm done with this class. So you know a rectangular waveguide basically looks like this. And it's a straight piece of pipe that has dimension A and a height B. And really, when we have a guide, normally speaking, the one end of the waveguide is actually just sealed. It's got a back plate on it. Do y'all follow me? So there's only one way for any kind of power or information to go down. It's that way. It's in the Z direction. And if you cut a hole in the top of the guide, and we haven't gotten to antennas, so this is a bit much, and you would drop an antenna down there. That antenna is going to allow power to be coupled to the waveguide. And let me do it this way. This is RS that has to do with the actual source impedance of the guide. And you wanted to use this as a transmission line. You all know what a transmission line is, right? Coax cable, basically you have a power supply, you have a certain length of cable, and then you have a load. It could be anything. It could be an antenna, it could be anything at all. But the transmission line is used to really conduct information or power from one source to another point efficiently, so it doesn't just escape all over the place. So if we're going to use a waveguide to do that, the first thing we have to calculate is the characteristic impedance of the waveguide. I'll call it Z0. And for a rectangular guide, it's almost always in the TE10 mode. Y'all with me on this? So the way you go about that is you don't want to excite any mode but the 1 mode. So the way it's done, usually in Whitmer's book, he's going to have it called eta of the guide. Something like this. Well, eta of the guide is nothing more than square root of mu over epsilon. And in most cases, it's eta naught, and that's 125 ohms, and I think everybody understands that. That's about it. Now, technically, you could say it's 125 ohms over the square root of epsilon relative, where epsilon relative would be the epsilon relative inside the guide. So you could say eta of the guide was actually equal to eta naught over the square root of epsilon relative. I'm just putting that there for some information. So when we calculate, when we calculate the characteristic impedance of the guide, first we have to, and this is typical, first we calculate the cutoff frequency of the 1-0 mode. If you think about that, that's typically C over 2. And then if you think about what goes in here, it's usually, it's M over A squared, and you take the square root. So it's just A, right? And let me just do this so everybody understands this. We can take a look at the cutoff frequencies of the guide for the MN mode. That's typically 1 over the square root of 2 pi. Square root of, I'm going to do it that way. It's 1 over 2 square root of mu epsilon, right? And then it's going to be square root of m over a squared plus n over b squared. Do you all know what I'm doing here? Right? Remember this? So this is really going to be for the f, the cutoff frequency for the 1O mode is going to be, or really c, I'll put c here, over 2 square root of epsilon relative. And then you're going to have simply times 1 over a. And if it's free space, if you're talking about air in the guide, then FC 1O is simply equal to C over 2A, right? That's the cutoff frequency of the 1O mode, and that's typically the dominant mode. Now we always, when we're doing this analysis, we're assuming the long dimension is on the horizontal axis or represents A. That's important for the cross-sectional area. When we have this, after we get the cutoff frequency of the guide, which in this case is going to be just C over 2A if it's air-filled, that's the way it usually is. Then we get the characteristic impedance of the guide, and I'll call it Z0TE10. And from that point on, I'm going to just refer to it Z0 here. So it's like the characteristic impedance you're familiar with transmission lines. And that is just equal to eta naught, or 125 over K. And K, of course, is going to be equal, this is for the 1O mode only we worry about. It's going to be equal to square root of 1 minus FC10 over the actual operation frequency squared. And I think everybody knows this, but I'm just going through it and I'm trying to be clear, right? There were people that I think had problems or got confused about some of this. K is just a useful constant because it happens to appear in so many things. For beta, we use K, correct, class? But K has to do with the mode it's operating in. Typically for a rectangular guide, you would operate it in the 1O mode, and F is the operational frequency. And the operational frequency has to be greater than the 1O mode and less than the 2O to excite only one mode. I think I've said this many times, and I hope it's clear. So we have this. Now the next thing you have to realize is when you're doing a problem where literally I'm going to try to represent what I've shown there in terms of the transmission line theory that you had before. So I'm going to say I have some RS here, and I'm going to have a source voltage. This isn't in Wentworth's book, so please write this down. A source voltage at a given frequency. This will be an assumed peak value. Then the guide itself is going to appear here. And the guide, you can think of the guide like you would a transmission line. Here it's got some characteristic impedance that I'm just going to call Z0 now. I know it's going to be greater than 125 based on the value of K. Y'all with me, class? I have that. It's going to have a certain length here, L. And I'm going to put a load here. And what I want is the voltage across the load, the current through the load, and what I'd like is the power dissipated by the load. Y'all follow me on this? So this is going to be, probably a lot of you know exactly what I'm going to do because it's going to be exact analogous problem as we would with a transmission line. There's a couple of things that change. And beta is the primary thing that changes this. So I'm going to put this down for you. I'm not sure this green is the best color, but something a little different. Let me switch it up and try purple. So if I use black, the problem with black is it's hard to erase on this board. So, all right, so here's how we do this. We need to first, you remember how you do transmission line problems? First, we need to get this V prime voltage there, right? Right at the beginning. Do y'all remember this class? And we'll assume the load is going to be at Z equals 0. So this point right here, if the guide has a link to L, this point is going to be Z equals minus L. To do this, who remembers the right way to do it? Well, the actual circuit you'd see is what? You're going to have plus to minus V Vs, you're gonna have the source right here, Rs, and if it did have an imaginary part, it would just be Zs, right? And then what you're gonna do is find out the input impedance to the guide, and that would be Zn right here. And that would be the input impedance to the waveguide. This is where V prime would actually be measured, theoretically. Can you all follow me now? How many know what I'm talking about here? You're a very quiet group today. What don't you understand?
No, I'm saying I like kind of remember it, like not. I don't remember
Well,
how to
you're
solve it, but
We're gonna go through it, and hopefully I'll be very clear about everything. You all, at least, it comes back in the EMAG 1, right?
so when you're saying the input impedance of the waveguide,
I'm about to write down the equation.
is it even when the waveguide is just air-filled, there's still some sort of
The impedance of the guide is a big function of frequency. If you remember, I'm gonna write it up here. What did I say? And
oh yeah, that's right.
I'm
Okay.
gonna call it just Z naught. It's like the characteristic
Yeah.
impedance of a transmission line. This one changes with frequency, right?
Yes.
So it's eta naught if it's air filled, or eta divided by square root of epsilon relative if it has a material in it. Then it's divided by k. And k, of course, would be the square root of 1 minus the actual cutoff frequency over the operating frequency squared. Okay?
Yeah, I forgot about that. Yeah.
I want to make clear that. Everybody with me on this one? Please be attentive. I'm going to give you a problem or two on this, but I want you to make sure you understand the steps. It's not one more spoke, but this is more directly applicable for what we do. So we calculate Zn, that's the input impedance to the guide. Make sure you get this right. So I'm going to use this Z naught as the characteristic impedance of the guide in the equation. So it's going to be Z naught, and then it's going to be ZL plus, and by the way, we're assuming losses. It doesn't make much sense to have a lossy guide. Why are you using it? I mean, that's the first logical question. There's a very low loss, but you don't need to consider it in this input impedance formula. We can deal with that later. So it's going to be ZL, the characteristic impedance of the load, plus, and it would be JZ naught. Now it's that Z naught, it's not 125. And then it's going to be times the tangent. Now write this down. It's beta in the guide times L. It's not just 2 pi over lambda. Y'all hear me on this? Unless you use lambda in the guide. Beta in the
Call
guide.
that beta Z.
Well, yeah, but I'm calling it beta in the guide, but you can call it beta Z if you want. You can. How about we do it that way? Beta Z, and I'll just put beta Z is equal to beta guide. That way, we won't have any confusion. Then it's divided by Z naught plus JZL times the tangent of beta Z times L. Before I go any further, I define Z naught. Now I'm going to define beta Z. How many know what beta Z is? We just did this. You do? Good. I'm not asking you to give it to me. Beta Z is the beta unguided, right? Times what? K, isn't it, class? That's the reason I've copied. K is used over and over again. That's the reason I like to put it one time. So beta unguided would be omega square root of mu epsilon over C if it's air-filled, correct, class? And then it's omega square root of mu epsilon. Now it's times K, so that's beta Z. Now you'll notice, now I have the input impedance, right? You agree? Once I have the input impedance to get V prime, it's simple voltage division. I have 2 impedances in series to get the voltage across Zn, which is the input to the waveguide. Now I can say that V prime itself is going to be the source voltage peak value we're going to use times Zn over Zn plus Rs. Okay? Y'all with me? By the way, did you get your quiz? It must have come in when I was on the board. Are you Zhang Li?
Yeah.
Listen, quite a few today, actually. At least I got 3 or 4 more quizzes. All right, so now we get V prime. Now, this is the key to the whole thing. V prime itself would be simply what I put there, Vs times Zn over Zn plus Rs. Many of you remember doing that. And that has to be equal to V0 plus, and here you're going to have E. Now normally it's minus J beta Z, or beta Z times, but here it's going to be plus J beta Z times L, plus the reflection coefficient at the load, and it's going to be e to the minus J beta Z times L. Let me also state that for this particular transmission line / waveguide model, the voltage anywhere on the line is usually given as V0 plus times E, and this usually is minus J beta Z times L, plus the reflection coefficient below times e to the plus J beta Z times L. Really not L, Z, pardon. I'm very sorry. Times Z. Are you with me? Do y'all remember this? And what is gamma L, by the way?
Reflection coefficient.
In one word, it's the, or two words, reflection coefficient, right? Where? At the load. You remember how to get it? Always the impedance you're going into, right? So you're here, and I'm going into ZL, so it's ZL minus the impedance you came from, Z naught. Now that Z naught is the characteristic impedance of the guide. That's real important. It's not 125. Y'all with me? Over ZL plus Z naught. In general, it's a complex number, usually.
Okay, so the Z naught on this side is the intrinsic impedance of the.
No, this is the waveguide impedance.
That's the waveguide impedance.
Intrinsic impedance is 8 or not. I don't mean to confuse you. The guide itself, if it's in the TE10 mode, has an impedance that's greater than air if it's airflow. If it's in the TM mode, a TM11 or something, then it's going to be 8 or not times K, which is less. Do y'all follow me, class? Now the impedance at cutoff for the 1.0 mode right here, K goes to 0 and it goes to infinity. Y'all with me? It's real important to remember that. So if you get real close to cutoff, you really can't couple any power. Just remember that. That way you won't do dumb things like a lot of people. You always want to operate it away from the extremes, from the actual 1.0 and the 2.0 cutoff frequency, somewhere in the middle, let's say. Okay, so that's the reflection coefficient. And typically, you know, what do you drive a waveguide with? Well, you drive antennas. That's one of the big things. Antennas are typical. If you're driving antennas, you got a lot of power. Waveguides will allow a lot of power in the microwave range to get down there and with a relatively low amount of loss. Really. Now, transmission lines, one of the problems is the field level. I'm just going to try to make sure you see this. If we take a look at a standard transmission line, we got a little core here, and then you have an outer diameter. I'm just trying to show you this. If you looked at the field values, just plotted the electric field, they call it, what do they call it, a vector field plot, you would see a very large field here as you got further away, it's smaller, almost nothing in relative scale at the outer point. Y'all with me? Very high in the center. Well, the dielectric breakdown in a region is the thing you worry about exceeding. So if the core diameter, then again, these things are small. If you want a lot of power there, what happens is you get this very large field, and most of the power is real close to the actual core for a waveguide, for a transmission line. You don't have you can't propagate a lot of power. Also, you have a lot of loss. So with a waveguide, it's rectangular. And if you plotted the field, say we're in the TE10 mode, so the electric field here in the y direction would look like this. Now that field will have no variation in the vertical direction. It'll be the same electric field magnitude from right here to right here. It'll have the sinusoidal variation. When you integrate the power density, it's, if you just take a look at the power flow, 1/2 E cross H. Take a look at that. And integrate it over here, you're going to find a whole lot more power can be sent with a rectangular waveguide of a given area, cross-sectional area A times B, compared to what could be sent with a transmission line with outer radius B, inner radius A. You all follow me? And that's real important. So that's the reason we use waveguides. Low loss, we can send a lot of power. Downside of working with waveguides is these are very rigid structures. Like, coaxial you can bend fairly easily without. Waveguides, there's some flexibility and stuff like this, but they're harder to deal with. And typically speaking, the tolerances are much more exact. You can't have any variation. If you just take a hammer and whack a waveguide and put a big dent in it, you'll get what's called a hot spot and you get impedance mismatches, and it causes a lot of problems. So keep that in mind. Some of you will work with waveguides, almost guaranteed. All right, now, y'all remember this equation? What do I need from this equation? The secret sauce, you might say. The secret, the next step.
V0 plus.
I gotta get V0 plus. That's the whole 9 yards, right? So I need to just reverse engineer this, you might say. Once I get V0 plus, I could write it down, but you can see it's just this divided by that, right? Go with me. Once I have V0 plus, that's all I need to get the rest of the problem solved, because now, does everybody agree you can get V0 plus here? If you know the load, if you know the length, if you know the frequency operation, the cross-sectional dimensions, say it's airfield, and you know RS and you know VS. Yeah, I can go ahead and I can get V0 prime. Now, to get the voltage at the load, which is critical, that's what we want. Voltage at the load is simply the voltage at Z equals 0. That's the reason I always make the load at 0, so the math is simple. And that's simply going to be, write this down, V0 plus times 1 plus the reflection coefficient. So that's the voltage at the load. It's usually complex. Magnitude and angle. Y'all with me? What's the current at the load?
That divided by the ZL.
IL would be simply VL divided by ZL. Now it's going to be complex. Y'all with me on this class? It's going to have a real and imaginary part, likely, or a magnitude and an angle. Now to get power, we could do 1/2 the real part of V times I conjugate. But the easy way to get power is this. I'm going to put it right here. If you want the power at the load, this is power at load, and this is average power. Simply go ahead and say it's 1/2, and write this down, magnitude of the load current squared, and it's times the real part of the impedance of the load. It would be, the resistance. Imaginary, if it's got a J omega L, if it's got some reactive component, they never dissipate power. Do y'all follow me, class? You know what I'm talking about? An inductor or capacitor does not dissipate power, only a resistor. And this is the easy way to do it. IL is easy to get. Usually the load would be like 50 ohms plus J 20 ohms. It's only the 50 ohms you're worried about. You all with me? You good with that? And that will work. I got a question for everybody. Just in case, suppose I asked you, what's the wavelength on the guide? Now, the way I do this is I think about the extremes. What is the wavelength in the guide at cutoff frequency? It's going to infinity, right? What is beta in the z direction at cutoff? 0, right? What is beta? 2 pi over lambda, right? Y'all, are you with me on what I'm saying?
But why is it infinity?
What? The wavelength?
Because it's not allowed to pass, so
Here's what's really happening. When I think about the wavelength on the guide, if you think about it, If the wave is just, suppose this is a plane, the plane the wave is in this direction, right? If it's going this way, the wavelength in this direction is going to be the same as free space wavelength. Does that make sense that way? Now, when it's banged in this way, and this way, the projection of the wave actually in this direction, the wavelength in this direction, is getting longer and longer and longer. And you might not be able to see this clearly, but when it's doing this, just think about this. When it's bouncing straight up and down, just move it a little. Look at the phase front, all right? Wavelength from here to here would be a wavelength, right? The projection in that at here, well, you can't probably see it the way I'm talking about, but it'll be infinite at cutoff. It literally, the wave is just bouncing up and down. There ain't no projection of wave. It's hard to see this sometimes, but play with it and I promise you will. Beta goes to 0 at cutoff. And wavelength goes to infinity. Hope you can follow me. Now, well, you can play with these things and you can see them a little bit better. Sometimes, I bet you YouTube has simulations that's really helped. YouTube has become my very best friend when I'm trying to explain topics that a good picture, especially some illustration that's time varied, is available on. YouTube is really good with this stuff. All right, that's how you would do a problem with a real waveguide. Y'all with me, class? And we could calculate all sorts of other characteristics like peak power flow and all that stuff. But this is primarily what's of interest.
So you said wavelength is 2 pi over beta?
Do you remember how you get wavelength, anybody?
You do 2a, 2 times a.
You say what? You assume sinusoidal variation, or else wavelength means nothing, right? And you know you're going to have a cosine of what? In general, it's beta times z, right? Let's just talk about free space wavelength. Do you all agree with this, class? Well, if you think about wavelength and you were plotting that, just the cosine variation here. Cosine of beta times z, that's 0. But you'd see it starts here, goes down, comes up, and where it begins to repeat itself is a wavelength. How do you get that? Well, that's 0, right? This has to be 2 pi. Right? It has to be 360 degrees. So you can say beta times the wavelength, this would be in free space, is 2 pi. Now if it's beta in the guide, right? Lambda in the guide. So beta in the guide, or beta z, lambda in the guide is 2 pi. 2 pi over beta z is equal to lambda, or wavelength in the guide. As when beta z goes to 0, you're at cutoff. When that's going to 0, this is going to infinity. It's getting longer and longer and longer. It's just a projection of the wave. Field equations, by the way, we can solve for the field equations, but remember, if you have EZ, if it's a TM mode, or if you have HZ, if it's a TE mode, you can just take the curls of those and get every one of them. And in Whitmer's book, he does that. He goes through and shows that. I don't even know, I think it's a problem in the back. I may give you that, but it's not that difficult to do. So, now here's what I'm going to tell you. By the way, the equation I was referencing for the waveguide impedance is on page 398. It's equation 7.79. If you take a look at that, if you want to write it down, or if you don't. Yeah, it's on page 398. The reason I'm telling you that, you may want to take a look at the reference in his book about it.
And then that's for TE mode. For TM mode, it's just eta times k.
That's right. That's exactly right. And the field equations he has are for TE and TM. I don't worry about that. In the undergraduate level, that is not that important, the field equations. I mean, solving for those. So then in Wentworth's book, what he does is have a slab wave guide. A slab wave guide is really, there's no metal. It's a piece of dielectric. And I'm gonna go through this, not today, but I'm just gonna show you. So they have a slab of material with some epsilon relative in it that's greater than 1. And what they really assume is the dimensions here are infinite. You might as well say that the separation distance here is infinite. So one dimension gets completely taken out of the equation. It's a slab. And there's another dimension here, A. Now I'm just prepping you for it. I'm not going to go through it today. Now when you look at this, and this is maybe hard to see, just think of it, a very thin piece of material like this that goes on forever in that direction, Z direction, all right? Here's what happens. If you looked at the side of a slab waveguide, and he has the equations, the fields just are like a rectangular waveguide, they bounce up and down. But what actually happens with the slab waveguides, the fields don't go to 0 at that surface. Y'all follow me? Two dielectrics, right? It's E tan 1 is E tan 2. H tan 1 is H tan 2. So you actually get a field, an electric field that extends beyond the boundary of the waveguide. Can you at least appreciate that? Now, that field is not propagating away. It's propagating, in a sense, it's not even propagating, but it's propagating along the z-axis. This is a hard thing to really appreciate as you see an illustration or a little cartoon of this stuff in real time. That's called an evanescent wave, but that energy is not propagating that way. It extends outward, but the whole wave is propagating down the guide. And what the guide really does, you might say, is act as sort of like capillary action, or like a surface tension, that it holds the wave inside the guide. That's sort of the way we can show this with the equations that we solve. And the wave just bounces down the guide. But the weird thing about a slab waveguide has no lower cutoff for the 1-0 mode. There'll always be, even when you're getting very low frequencies, that guide will tend to hold the wave and it will just propagate more or less centered on the slab. I'll go through the equations. They get a little hairy, but I don't want to do that today because that gets a little. When I start doing the math on this one, I'm going to tell you where it is. He shows the slab waveguide, starts on page 404. He does not go into and explain why it's important to know what mode is propagating. In your own words, why would it be important to know only one mode's propagating? Anyone?
Why is it important to know which mode is propagating? Well,
What if you had two modes? What would be a problem? Anyone?
They can both go at the same time.
The velocity that they propagate is different. Some of the power is moving at a certain velocity, the other power in the other mode is moving. So when you try to reconstruct that at the end, it's going to be garbled. It'll be something like aliasing. Y'all with me? No coherent processing. You only want one mode, which means you got to be below what's called the lowest cutoff frequency. That's the 1-0 mode. I'll spend time on that, but there is no lower cutoff. And the equations I think that they have in there for this, I hate to say it this way, but they don't really do justice to try to explain what's going on. These equations mask so much of the stuff. And he shows you the field equations. If you don't have somebody that can talk about this from a perspective of how it really applies and what you need to know to do it, it's not going to make a lot of sense. Where they use slab waveguides is in like optoelectronics when you have these. You've seen VLSI processing, right? So if you have you know what a photodiode is, don't you? When you have that and you want to get information across points on a chip at very high frequencies or photonics, you're using just clusters of photons in a chip, then you use slab waveguides, or you use fiber optics. Fiber optics is like just the cylindrical fiber guide, right? Y'all know what fiber optics are, right? Have y'all been around fiber tube or anything like that? That's what I want to do today. I actually want to tell you that there's a lot more I could tell you about this, but fiber optics, optical fiber is on page 407, and I'm going to tell you that I want to first give you a little perspective, my perspective on this. The real reason optical fiber is so important is it's not the power they can handle, not that at all, but the attenuation is so extremely small, and you can propagate frequencies that are so much higher. It is a piece of glass, is what it is. You know, fiber optics actually is making the inner core of real fiber optic is silicon glass. Y'all follow me on this, class? And it's hard to bend, but DuPont and Dow Corning, they're material scientists, they add things so you can bend it a little. But has anybody seen real fiber optic cable being put into the ground? Depends on the year, but what you're going to see is a cable, depending on the type, but real fiber optic cable, like for Verizon, you're going to see a core about that big. Is this the one you're thinking about? This? Are you talking about real fiber optic that's put in the ground, or just
overhead fiber optic cable as a
hanging? That'd be smaller. But I mean, some of this stuff, real short range stuff, is just plastic. But the stuff that is in the ground and stuff like this, that is something about this big. They have it on a giant spool, and they unroll it very carefully, and they put it in the ground, and it can handle an enormous amount of information, phenomenal amounts of information. And the attenuation, the rate that signal decays, is literally like dB per 20, 30 kilometers, a couple of dB, almost nothing. Coax cable is like 4.5 dB per 100 feet. It's ridiculous, and that's just at a low frequency, yeah.
You said the core is that big or the whole line?
Well,
The core itself is that big?
No, what they do is they have something,
There's like cladding and stuff.
at first they have this cladding on the outside that's protected.
Yeah.
Then inside of that, they're going to have some other materials that cushion it or something like this. Then they're going to have the core, and the core diameter is something we'll talk about. But there are the multi-mode and there's single-mode fiber optic. Multi-mode means that it can have more than one single frequency going down there, or the photons don't have to be a single frequency. And there's some spread in the actual, there is some dispersion of velocity curves. But single-mode fiber optic is the thinnest, and it's actually the most expensive, and the one you would like. Now, now I'm going to have to first go into fiber optics, the calculations, and show you some basics. We don't do this from the point of view of solving Maxwell's equations for a cylindrical guy. We probably should, but that's a little beyond what we're going to do here. At the graduate level, at senior level stuff, if you take any kind of electromagnetics course that deals with fiber optics, I'm sure, you know, Masood, I don't know, do you know who I'm talking about? Masood upstairs. If he was actually teaching this course, a senior level electrons, then he would do the derivation, I'm pretty sure. But at this level, I think it probably would not do much good. So
What chapter's fiber optics, 7 or 8?
it's in chapter 7. It's going to be after slab waveguide. We did rectangular conducting waveguide, and then we skipped slab waveguide for now. I just gave you sort of a big kind of a picture of it. Now, after that, you can take a look at that, and you'll see fiber optics or optical fibers, I think. Isn't that the next section? You see it or not?
What, after slab?
Give me page number 1 second.
There's fiber, optical fiber, then there's fiber optic communication systems.
Yeah, but you just want optical fiber. So that's
407.
7.4 on page 407. So he shows you the thing. What I want to show you is this, and this is in his book, picture he uses is he just shows the general form of jacket, cladding, and fiber core. And hold on. So let me do it this way. Typically, you're going to have a core, an inner core with a dielectric to it. And this is called a fiber core. And it has a certain diameter, I'll call it A. Radius. So it's this radius of fiber core. And it's going to have a certain epsilon value. And I'll call it epsilon of the core and intrinsic impedance, or no, I just call it eta of the core for now. And this just is, or eta relative of the core. Then outside of this, you're going to have another thing, and this is called the cladding. And that's going to have some epsilon relative of the cladding. I'll explain what I'm saying. Then around this whole thing, there's a material that he shows, and it's just to prevent critters from eating it. It's called a jacket. It doesn't have any bearing on the electromagnetic properties. Can you at least get appreciation? You got a core, fiber optic core is going to have an epsilon relative higher or larger than the actual cladding's epsilon relative. And he won't use epsilon, he will use the index of refraction, which is the square root of epsilon, in his discussions. And let me show you that. I don't want to rush it. He just uses N fiber and core. Okay, so in his book, what I'm going to do is this. I'm going to just use right down the pipe look at this. I'm going to go down the axis of the wire. So here we have some radius A, and this is the fiber. And we call it fiber core, and it has some index of refraction NC. And I want to make sure, I'm sorry, NF. Pardon, NF. His symbol he uses NF, and this is the index of refraction of fiber core. And that is really NF is equal to the square root of epsilon relative of the fiber core. Then he's going to have an NC, and this is really, I put CL there, it's the cladding. And this is the index of refraction of cladding. And he uses NC, and that's simply square root of epsilon relative of the cladding. Typically these are glass, so there's going to be out here, there's going to be another, and this is going to have a diameter B. This has NF, this is going to have NC, and that's the cladding index of refraction. It's not impedance. Y'all with me? I'm just trying to make it clear. What really happens is this. If we look at a cut, take the wire, cut it down the middle, and just lay it out, we have something like this. Here's the fiber core, or here's the fiber, and here's the cladding. And typically, they'll draw like a dotted line right down the center to show you where it's cut. And here's something that happens. Hang on. I'm going to try to be as clear as I can. So what happens is, this is not drawn as well as that line. Okay. This is diameter A of the core. Now, if you look at this, light has to get into this thing, so I'm gonna make this the boundary. Here's the core where I have this purple, put a little hash. This is the core, and that outer region there is the cladding. Here's what happens. I just want you to get a feel for this. You got light coming in here at certain angles, and I don't know how it's going to do this exactly, but I'm going to assume you got a rate. This is the normal. You're going to have some angle here that is going to be actually the angle associated with the light optical, say it's T wave or TM wave. This angle, I'll call it, I think he calls this theta A. And that is the angle that the light or the optical signal is assumed coming in. Y'all with me? Now it goes from a less dense medium, almost always this is air. Doesn't have to be, but almost always. You with me? Now you remember one of the things is you go from a less dense to a more dense region, it bends. Y'all with me? And it bends more towards the normal. So here, you're going to have another angle. And I'll call that theta B. That's just the angle it's going to bend. We can get that angle from Snell's law. Do you agree with that? It's coming in, it hits, bends. Now it hits and it hits here. And it's going to bend. Remember, that's the cladding this way, right? So, if you think about that, just trying to make sure I'm consistent with what his notation is. I think I am. He's showing this, the diagram I'm trying to show you on page 410. It's figure 7.22. And he's going to call this right here theta C. Are you with me? Now, the deal is this. For propagation to occur, you have to make sure that all the light that hits here reflects back. So it gets in, that's not a problem usually. Now it comes and hits all the stuff that comes in here. None of it can reflect out. Because if it does, it's lost. It would be a loss. All of it has to reflect back in. Does this make sense to everybody? So we start with Snell's law. And we're going to go ahead and get that angle things in terms of the critical angle. One other thing. First thing I'm going to do is do the relationship between these two angles based on Snell's law. So I'm going to look at theta A and theta B. Call theta A, theta B. So at that point, I know usually it's beta in region 1, which is air, right, times the sine of the incident angle with respect to the normal is equal to beta in region 2 times the sine of the angle theta B. Or I can say beta in region 1, which is air, times sine of theta A is equal to beta in region 2 times the sine of theta B. Can y'all follow me on this one? Now, because beta in general is omega squared of mu epsilon, that appears on both sides. I'm putting this down only one time, I won't afterwards. Times square root of mu epsilon, or mu naught epsilon naught, times square root of mu relative, which is 1, times the sine of theta A equals beta 2, which is omega square root of mu naught epsilon naught, times the square root of epsilon, and this is the epsilon of the fiber right here. It'd be the relative epsilon, times mu of the fiber will be 1 times the sine of theta B. The only reason I did that is to show you the omega, the square root of mu naught, epsilon naught goes out. What's remaining is, this is typically given as what would be the index of refraction of the first median. It's almost always air, so I'm going to leave it as air. Sine of theta A is equal to, the omegas cancel, the mu naught cancels, is equal to, and this is going to be, now this is the actual index of refraction of the fiber times the sine of theta B. That's A and that's B. Good? I mean, do you all follow me? I think this is in the book. I'm not sure how he does this, but you're going to see that the whole thing comes out. Now we go to this boundary right here. That green is not showing up the way I'd like it, but we'll work with it anyway. That boundary, the second boundary, here's what they want. Do this. I want to erase this. Work right here. Try to keep a little pitch, but this is actually interesting. So here's the second region, right? And here, this is the cladding, and over here, this is the fiber. This has an index of refraction beta called NC, and this has N of the fiber. Now, here's the normal. Here's the angles coming in it, and that was, he labeled that theta C, right? What he wants is this angle here to be 90 degrees. I'll call it, that's theta C, call it theta D, into the cladding. You understand that, everyone? So that means if it's 90 degrees or more, everything reflects back. Nothing is transmitted into the cladding. That's the idea. So Snell's law for this one is in the first region, it's going to be just the index of refraction, square root of epsilon of the cladding, times the sine of that angle, which is theta C, is got to be, I mean not cladding, of the fiber, pardon me, of the fiber, it's got to be equal to the index of refraction of the cladding times the sine of 90 degrees. That's the point. You with me? This angle is going to give us the maximum angle that this one can come in. This is real important. So just work with that. Come over here, and now I can see sine of 90 is what? 1. So I can see the sine of theta C is equal to NC over NF. And he should have that in his book if you look.
He calls it the critical angle.
It is the critical angle, because 90 degrees or more, I mean, when you hit 90 degrees, if you come at any angle larger than that, everything must reflect in. You all with me, class? Are you with me on this? So work with me here. I have this, right? What I want is this, but I got this sine theta B. So now, follow me on this. Just look at this drawing for a second. It's not very big. Maybe I should blow it up right here. So I have a triangle. That's a right triangle. And this is theta C, and this is theta B. Right? Now, if I look at this, the sine, right, of theta B is equal to cosine of theta C. If you look at that. Isn't that right? Take a look. If this is the hypotenuse, right? Just think about this. And this is the adjacent, this is the opposite. Well, if I look at this, the sine of theta B would be y over hypotenuse is equal to cosine of this angle. Cosine of this angle is going to be y over that. Y'all following in this class? So if I know that, there's probably other ways to get this. I come over here, and I said, well, I've got this. What I'm going to do is the old trick. I'm going to square it. So I get a, I think he does it this way. Sine squared of theta C is equal to NC over NF. squared, you all with me? Just squared. Well, sine squared is always equal to 1 minus cosine squared of theta c. Actually, I think I can do it that way. So, are you with me so far? So if I come over here, now I'm just gonna rearrange it. And I'm gonna say cosine squared of theta c is equal to, just take that to the other side, 1 minus the sine squared of theta c. And therefore, cosine of theta c is equal to square root of 1 minus the sine squared. I'm sorry. That's wrong. I want just cosine of theta c. See that over there? Because I'm going to substitute in that for sine theta b. So if I take a look at this, yeah.
Maybe 1 plus.
Sine squared plus cosine squared is going to be 1. That's, so, I'm sorry, this is what I got. That right there. Right? You'll follow? And so if I want cosine squared, that's what I actually just want. Cosine, I'll go cosine squared of theta c is going to be equal to 1 minus NC, that's the cladding over the fiber squared. And so cosine of theta c is equal to square root of 1 minus NC over NF squared. Now I take that, and I can see that the cosine of theta c is equal to the sine of theta b. Are you with me? And that's where I make the substitution in here. Now I can say, you need to write this part down. The sine of theta a is equal to NF times the sine of theta b, which is this, which is going to be square root of 1 minus NC over NF squared. And I think you can take the NF through, and that's the way he does it in the book. You can take the index of refraction of the fiber inside, he has a square root, and this will be of NF squared minus NC squared. And that's the sine of theta a. Now, there's something I didn't say. I assumed, I mean, I did say it, but I assumed this was air. If it's not air, you're going to have the index of refraction of A in there. And it'll have that in this book. But this right here, he's going to have this divided by, I think, eta 0 or something, the index of refraction, not eta, but n0. And that's equation 7.109. Almost always it's air, so I hate to put that in. For me, you're not going to get anything but air. Now, that is called the actual, it has to do with something called the acceptance, the actual symbol for this. It's called a numerical aperture. And NA, but it's the sine of the angle. Now, please just follow me on this. And you should have that down there, this numerical aperture somewhere. It's on page 411, equation 7.110. Here's why numerical aperture is so important. Like NO that he has there is the index of refraction of the media it's coming from outside the fiber. Guaranteed, it's almost always air. There may be exceptions when you have some sort of a plastic fitting or something keeping the spacing, but almost always it's air. It doesn't have to be, but almost always. That's as far as that. The numerical aperture is a measure of the, quote, goodness, how well it performs. The bigger it is, it means the less alignment you need with the fiber. So here's where, I don't have a lot of experience with this. I just want you to know, this is not from a lot of personal experience, but this thing I do know about the alignment with fiber. So if you take a look at a real fiber like this, and you're shining, say you got a laser, typically a laser, and you're shining it right down the hole like that, it'll transmit that, and if you look at the other end, it'll be lit, it'll be red or whatever, blue, whatever color laser you got. You with me? Now if you got real fiber and you start moving this thing like this, cocking it up, where that angle of incidence is getting less and less, there'll come a point where all of a sudden no light coming out. Now you've exceeded the sign, you've exceeded this. Whatever this is, the sign of that angle. When you take the inverse of this, inverse sine of that a to f squared minus a to c squared, it might be 5 degrees, 2 degrees, 3 degrees, 5. The larger that angle, the better. And here's why. That means the alignment doesn't have to be that critical. Now when you align these things, you have to understand, fiber is super thin. 5 microns, 10 microns thick, all right? You got another piece over here. You're going to have to align that thing of the order of microns of accuracy. And remember this much, when you have a laser and coherent light, it comes out at just one angle, basically. Does everybody understand that? Not all. I mean, there are gas lasers, you get some dispersion, but optical lasers that are, I mean, like gallium arsenide and stuff like this, if you're using solid state stuff to get a lasing beam, I mean the photons, the alignment is critical. And that's why the larger the numerical aperture, the better. That's my take on it. I'm not an expert, but that's the key. And that's why that is a measure of, quote, the goodness, the numerical aperture. Now, take a look at this. How good is it when NF is NC? You get 0. What's the inverse sign of 0? 0. You can't align. You with me on this one? You would like this to be as big as possible. And you can't get it as big. I mean, basically, there's really small differences. And you know what? He'll probably have this in here in an example. Very much got to work with. You have to align it perfect. Has anybody ever worked with real fiber optics and try to align? You have? Did you have, now tell me about this. Did you have experience working for a company doing this or personal just play with it?
Company.
When you were doing it, were you part of the guy that did the setup where you actually fed it with a signal?
No, I saw them splice 700 strands back together.
All right, that means they had to fuse them. All right, they have to melt the silicon. And I try to tell you this much, I don't have experience in that area. Most of this is really material science. When you get into fusing glass and all that, it's not a trivial thing to do this. And when you break fiber optics long ago, it was very expensive. You had to replace tons of line. Now they do have something where you can fuse it, and it will not, it basically is like almost welding the thing, but the weld is something that will allow the same index of refraction to be there. You have to make sure the diameter doesn't change, or the cross-section doesn't change much. That's sort of fiber optic in a nutshell. I want to tell you one thing. There are,
So I'm assuming that NF has to be larger than NC.
has to, or nothing works. Has to, as a matter of fact. Fiber core was always larger. There's two things that I have to say about this. That's sort of the, that's the guts of how you actually get this. You notice there's no Maxwell's equation, no solving, boundary conditions and all this. Fiber optics is something, we assume that these things were just tracing photons. We're doing optics. We're not doing any kind of electromagnetic engineering per se. Now, there's more to that. This is way beyond the scope of what we can cover here. So there's a couple types of fiber. There is a fiber that works in only one mode. That's single mode fiber. And then there are multi-mode fibers. The only one you really care about is single mode fiber. Then there's another type of fiber called a graded index fiber. Here's what I mean by that. I just want to expose you to some of the terminology. You may not remember all of it, but you need to be exposed to it. Because in the real world, I don't know how many people are going to be working around fiber optics. I know if you're doing anything that has to do with comm links and stuff like this, you're probably going to work with fiber optics. My first experience was in Huntsville in 1990. We were testing something called a multiple launch rocket system and its ability to withstand lightning strikes right before the first Gulf War. Well, all the current probes that we put on these tubes, that were fiberglass based, they're called B-dot probes. They're very fast magnetic field sensors, but the way we relayed information from the probe was with fiber optic lines. It was my first time I ever dealt with fiber optic lines. They're amazing. They don't have EMI, it doesn't interfere with it. You know how you have had to at some point in your life have something like a hair dryer going and there'd be lines in the TV, or you could hear it crackling on your phone or something like that. You know what I'm talking about? That's electromagnetic interference. Fiber optic there's nothing that the signals, any kind of static, lightning in it, will interfere with. It's just photons. There's no interference. And it's amazingly insensitive to any kind of electromagnetic problem in dealing with external interference, unlike our phone lines and stuff like this, the old legacy phone lines, which makes it perfect. A lot of things are perfect, but it's hard at times to get the stuff to actually fit and stuff. Fiber optic is sensitive to geometry, and if you splice it, it isn't like tying a wire together. Much, much different if you cut it. Now, when we talk about graded index fiber, I'm aware of the time. Here's what really happens. Here's the outer cladding, and here's the core. All right. Now, instead of having the core be whatever you call it, constant value of the intrinsic impedance, what it'll do is at the center, the core may have if you were to plot versus, say, this distance, the actual index of the core or the fiber, there may be a peak there, and it goes down to about this value as you get out. That would be the radial distance. You all follow me? It's called graded index. Now it doesn't have the same index the same intrinsic impedance. It basically, what they really do, they'll probably show something like this. It doesn't go from one value to the second. It comes out as you get closer to this point, it starts going from a high value to a low value, and there's a transitional point. So it isn't abrupt. It's called graded index fiber. And again, he doesn't even tell us what's so important about it. But the thing is, that's easier to make than step index. And it's used for multi-mode fibers. Graded index is shown on page 413 at the top. He gives you a little diagram of it, but I'm going to level with you. I don't have enough experience on that to talk about the real benefits. It's cheaper to make, that's the basic thing. But it is multi-mode. It will not conduct just one mode. The only thing I'm going to ask you about, the last thing I'm going to tell you is, with fiber optic, the real thing, don't worry about the number of propagating modes and stuff like this. You can't even solve the equation to get this. But if you look at equation 7.103, I won't put it the way he does it, there's one critical thing. You know how the TE10 waveguide, getting that 10 cutoff frequency is the key thing. It's essential that you know that. Because you have to operate above that, and then the 2.0 is just twice that. You with me on this, class? Well, the critical thing for fiber optics is being at a frequency that is only going to propagate or allow one mode to be developed. And that's called, and what happens is you get something, in his book, he's going to call it the thickness that will allow only one mode, and how does it call that? In step index optical fiber, only one mode will propagate in free space if the free space wavelength is big enough such that he's going to have this. So it's a low frequency. Larger the wavelength, lower the frequency. You all with me? So this is called a frequency below which, so the photons would be below that. and he calls it theta A is equal to, I'm putting it the way he does it because there's probably other ways to write this. They're slightly different. A, again, is going to be fiber radius. And then he's going to have times the square root of n fiber squared minus n core squared. And it's going to be over something that we don't even discuss other than it's a constant. It's called K01. It's the zero, the first zero of the zeroth order Bessel function. You have to just take that for granted. It's 2.405. Now, what does that really mean? Not a lot to you. It's a text. It's really like a technician's equation. But here's where it comes from. If you were to go ahead and solve, you know how when we solve for the cutoff frequency for P1 mode, remember when we got the expressions for, we broke up the E field easy and we got those sine of beta x times x, sine of beta y times e to the minus j, beta z times, do you all remember that? And we found out what? That beta z or beta x itself had to be equal to m pi over a, and beta y had to be m or n pi over b. Do you all remember this? So, if you think about that, if you had a fiber optic and it was cylindrical, when you do the del squared of Ez plus, and I'll call it beta unguided squared of Ez, and set it equal to 0, and you solve this, when you do separation of variables, your radial distance variation, rho, with that, remember, you got a cylinder, would have something called a Bessel function. And you would get a separation where you have Ez is going to have a form of J, just going to have to work with me on this, J0 of some beta rho that has to do with the radial variation times the radius. Just, I'd love to do this whole thing, but it would take a full lecture to go through. All right, this is a Bessel function. And the Bessel functions, for a zeroth order Bessel function, it sort of looks like this, and it goes to 0. Now, you know the 0 is critical, right? That is the first 0. That K01 has to do with this value in a Bessel function solution that is well beyond what I can discover. But that's where this silly thing comes from. And this has to do with like the dimension A. You remember how, this is a circumference, by the way, it's 2 pi A is the circumference of that one. And it gets more complicated, but I'm trying to tell you, this actually comes from a scientific formula, and it's deducible. It's not just, well, it works. I'm trying to tell you that because he doesn't do it in there. Now here's what's going to happen, right? I'm going to give you some problems with fiber optics. You will not be responsible for gradient index fiber or how many modes in a multimodal fiber. The only thing I want you to be able to do is if I gave you that little dot here and I said, calculate the numerical aperture given this value for the two fibers, core and fiber index, you should be able to do that. You got that? I'd even go as far, now I'm not going to give you the formulas for that, but for the numerical aperture, I'll even give you that formula. Now that, just what I just told you is you don't need to do any kind of ray tracing if you have that formula. But we might ask you for A or angle B or something. I'll give you problems that are represented. I don't worry about multi-modes and number of modes because that stuff is actually worthless. So on Wednesday, I'm going to sort of finish up this chapter because we're not going to do the fiber optic link. I'm not going to. But what I'm planning on doing is getting into electromagnetic field. I'm going to get into chapter 8 Zencastr. Okay, sweet. I don't mean to sound, a little irritated, but fiber optics, if you're going to do it right, you need to do the full field equations. If you really want to get immersed in it, he just wants you exposed to it because you guys are going to be out there in the real world working with this stuff. And you really look like idiots if you don't ever even heard the term. Wow. This lecture makes sense to you too? Mostly,
You didn't cover it last semester, but
yeah.
you didn't cover,
Slabs,
you didn't cover,
transmission.
whatever this is called.
This is for optical fiber.
Yeah, you didn't cover that.
I did something on optical fiber. I know I did.
Hey.
I didn't give you
There was,
I'm-
there wasn't like a question on an
no,
assessment.
I'm not gonna ask you to test or quiz, that kind of stuff, because frankly,